Hi guys, so this is the second part of the Science 2022 paper 1 that I started. So this is the second part. So I'm going to start from where we ended. So in the last lesson we looked at that was section A, multiple choice section. Now we start from section B. So let's start. B1, figure B1.1 shows part of a micrometer screw gauge. So this is a micrometer screw gauge. Then they're asking us to say what is the reading on the micrometer screw gauge. How do you find reading from a micrometer screw gauge? So from a micrometer screw gauge, you need to find this reading first that we call the sleeve reading. We call it the sleeve reading. Now it is at 20, so it is at 20.00 millimeters. Then you check for this reading that we call the thimble reading. You can also call it the circular reading. Now the thimble reading, this is how you read it. You check for the reading that goes in line with the reading from the sleeve reading, and this is 30. Now that reading, you multiply it with the accuracy. Now the accuracy of a micrometer screw gauge is 0.01, and if we say 30 multiplied by 0.01, we get 0.30, like that. Then from there, to get the total reading, we just add the two together, so we have 20.00 millimeters. Then we also have 0.30 millimeters. So we add these together so that we have, so the decimal point in the same line, so we have 30 millimeters, then we have 20, so we have 20.30 millimeters. So that is the answer that is supposed to be put here. So the final answer is 20.30 millimeters. We go to the second one. So the second one, we have a question. State one use of a micrometer screw gauge. So one use of a micrometer screw gauge is to measure the thickness of a laser blade. So we can say we can use the micrometer screw gauge to measure the thickness. So to measure the thickness of a laser blade. So we can use it to measure the thickness of a laser blade. So that is one use of a micrometer screw gauge. Okay, so we progress. We look at another question. We have B2. We have a question there. Figure B2.1 shows an object first weighed in air, then when it was immersed in water. So we have an object. So this side, when it was weighed in air. So here it was weighed in air. Then here it was immersed in water. So you're able to see the differences. So now here is the thing. So measuring first weight, so we need to find out what is happening here. So let's come down. We say determine the weight of the stone in air. Okay, they are measuring weight. So weight is measured by a special instrument we call a spring balance. So the weight here is 60 newtons. The weight on the other hand here is this is 20 newtons. Weight is measured in newtons. So the weight in air is 60 newtons. 60 newtons. As simple as that. Then the other one is a definition. Define the term upthrust. Define upthrust. Upthrust is a force. So upthrust is a force. So we can simply define upthrust as a force that is a force that opposes. So upthrust is defined as a force that opposes the rate at which objects sink in a liquid. So the rate at which objects sink in a liquid. Now there are many definitions you can give for upthrust, but looking at the number of marks there, that one is going to work just fine. Okay, so from the diagram shown in figure B 2.1, determine the upthrust of the water. Now this is easy. To find the upthrust of the water, what we do is we're just going to get the difference between the two, because the weight of the stone in air was 60 newtons. Then the weight of the stone when it was immersed in water, it became 20 newtons. So this difference is going to give us the upthrust. So the upthrust is a difference which is just 40 newtons. After finding that, we proceed, calculate the mass of the stone. Now how do you find the mass? Now remember, we can find weight as mass times gravity. Then if we say divide by gravity, then the mass of the stone can be found by saying the weight divided by gravity. Then the weight of the stone, originally the weight of the stone was 60 newtons. Then gravity, they've given us 10 newtons per kg. 10 newtons per kg, the newton is gone. Then 10 into 60 is 6 kilograms. So here we just find 6 kgs as our mass. So 6 kilograms. Simple as that. We proceed from there. Look at a different question. So we have question B3. Now question B3 is a question we are having a thermometer. So we are saying figure B 3.1 shows a device used to measure temperature, and this device is a thermometer. Define thermal expansion. In simplicity, thermal expansion is defined as the increase. So this is defined as the increase in size. So the increase in size of a substance, increase in size of a substance due to heating. So the increase in size of a substance due to heating. So that one is thermal expansion. The increase in size of a substance due to heating. So that is how you can define thermal expansion. Proceed, identify the parts labeled E and F. So part labeled E, so we start with this one. What's the name of this part? So this part, it is called the bulb. So that part is called the bulb. Then part F, this part is called the constriction. So that part is called the constriction. Just like that. Now, we proceed. Name a liquid that can be used in the device shown in figure B 3.1. Now, in a thermometer, the liquid that can be used is we can use mercury. mercury can be used. Apart from mercury, we can use alcohol. So you can pick one, mercury or alcohol. Mention one way in which the sensitivity to the device shown in figure B3.1 can be improved. So how can you improve the sensitivity of a thermometer? Now, sensitivity of a thermometer can be improved by using what we call a narrow capillary bore. So if you can say, so by the use of a narrow capillary bore, let me just say a narrow bore. So by using a narrow bore, you can increase. Now this is not the only reason, but the question is saying mention one way. So you can also put any way that you can think of, and it can just work out fine here. Okay, so we proceed. We look at we have question B4. Two successive crests of approaching water waves are separated by a distance of 1.8 meters. It takes 0.3 seconds for one crest to cover the distance of 1.8 meters. At what speed is the wave traveling? Now, we want to find the speed of a wave. Now, speed of the wave given by V is equal to frequency multiplied by wavelength. Alright, but remember, frequency of a wave is given by 1 over period. Okay, now let's do this. I'll say the speed of the wave, while there is frequency there, I'll put 1 over period multiplied by the wavelength. Why? Because I've not been given frequency, but I've been given period. Period is a time taken. So the time taken is 0.3. So 0.3 multiplied by the wavelength, just a length, which is distance, 1.8. So 1 over 3. Now 1 over 3 is 3.33 multiplied by 1.8. 3.33 multiplied by 1.8, we get 5.99 meters per second. So now 5.99 meters per second, this can just be rounded off to 6.0 meters per second. Just like that. So meaning we have found the speed at which the wave was traveling at. Then what distance is covered by the wave in 2 minutes? Distance, so we can do this. Distance is equal to speed multiplied by time. Okay, since speed is equal to distance over time, so if you make distance subject, distance is equal to speed times time. Then the speed there, we already have the speed. So if I get the 6.0 for speed, then the time is 2 minutes. So we convert 2 minutes to second. In 1 minute there are 60 seconds. So in 1 minute there are 60 seconds. What of in 2 minutes there are x. So x is equal to 120 seconds. So this multiplied by 120. So what we get when we say 6 multiplied by 120, we get 720 meters. So this this 720 meters, this one is the speed of the wave, or the distance, the distance of the wave. We proceed, we look at part B1. Calculate the frequency of a sound wave with a speed of 340 meters per second and wavelength 0.5 meters. Alright, now remember, speed of a wave is equal to frequency times wavelength. then frequency will be equal to speed over that. Okay, then the speed of the wave is 340 meters per second. Then the distance is which is wavelength, 0.5 meters. So 0.5, this is just more like saying 340 divided by half. So we get it's multiplying by 2, so we are going to get 680 hertz. So capital Z small letter, capital H small letter Z, so 680 hertz. So you write it here, 680 hertz. Okay, so that one is done. We proceed. Could this sound with a frequency calculated in B1 be heard? Can 680 be heard? The answer is yes. How can we justify our answer? So we are saying yes, it can be heard because it is within the range of audible, is within the range of audible frequencies. So it is within the range of audible frequencies. That means it is between 20 Hz all the way to 20,000 Hz. So 680 Hz is in between those. So yes, it can be heard. So anything between 20 and 20,000 Hz can be heard. Right, we go to another question. Question B5. How can we answer that question? Infrared and radio waves are components of the electromagnetic spectrum. The first question, mention one use of each of infrared radiation and radio waves. So one use. So what can we put for infrared? So infrared can be used in remote controls. So this one is used in remote controls. It's used in remote control, so you can actually put that one. Then you can also say radio waves. Radio waves can be used for telecommunication, so this can be used for telecommunication. Of course you can put other uses, but I'm just picking one. I'm just going by one use. Of course there are many other uses of these waves. Okay, mention one common property of infrared and radio waves. One that is common for both. So one common property is that they are both electromagnetic waves. So we say both are electromagnetic waves. Both are electromagnetic waves. So that one is common. We can also say they both travel at the speed of light in a vacuum, but let's just leave one for now, which is okay. Then we go to another one. What is the other question saying? Give one harmful effect of electromagnetic waves. What is an effect? So one harmful effect is that they can cause cancer. So they can cause skin cancer. So that is very dangerous. Alright, give one difference in propagation between sound waves and electromagnetic waves. So what do you think is a difference in propagation? between sound waves and electromagnetic waves. So what we are saying is that for sound waves, so for sound waves, in order for them now, they need a medium. So these sound waves, in terms of propagation, they need a medium. So they need a medium. But for electromagnetic waves, so for electromagnetic waves, they do not need a medium. So do not need a medium. So they do not need a medium. All right, we proceed. We look at another question. Mention one factor that affects the loudness of a sound wave. So one factor that affects the loudness of a sound wave is called amplitude. So one that we can put is amplitude. So just one is enough. Just one is enough. All right. Proceed. Look at another question. Learner sees a flash of lightning and hears the thunder after 4.5 seconds. How far is the lightning from the learner? Take speed of sound in air to be 340 meters per second. So if they say how far, they are looking for distance now. But remember, speed is equal to distance over time. Then we can find distance by saying speed multiplied by time. The speed they've given us 340. Okay. Then what of the time? So the time has been given to us as 4.5 seconds. 340 multiplied by 4.5, we get 1530 meters. So that is the distance that is taken. Very much important. Alright, so that one has been done. We proceed, we look at another one. Question B6. Figure B6.1 shows magnetic field lines between the poles of two magnets. Name point R. So point R, this one is nothing but the neutral point or point of no magnetic effect. So we just call this as the neutral point. So that one is called the neutral point. That is point R. Then if P is a south pole, what are the poles Q and T? So now look at, if this is a south pole, then this one becomes a north. Then what are the, okay, so Q is north. Alright, what of T? Now look at, these are not attracting, these are repelling. So these are repelling, they're not attracting. So meaning, in order for them to repel, it means this is also a north pole. So north are going to repel, then this becomes a south. So T is a south pole. T is a south pole. Okay, we proceed. We look at another question. Question 7. Question 7. Figure B7.1 shows a graph of voltage against time when charging a phone battery. So that's the graph that we have. So we are actually looking at this graph here. Then the question is, what was the voltage in the phone at the start of charging? So this is where the start was. So now this is where the start was. So at this start, the voltage was 2 volts. So at the start, the voltage was 2 volts. Simple and straightforward. We go to the other one. How long did it take the phone to reach full charge? So in order for the phone to reach full charge, how long did it take? Now let's go on top. Let's go on top and find out how long. How long is time? So we're saying the phone reached at full charge, so somewhere here, because after this point the graph was constant. So here the phone was full, so you just go down and check the time that you're going to find there down. Then that is actually the time it took for it to be at full charge. Okay, so you come down and you check and you discover that it is somewhere the middle between 3 and 4. So between 3 and 4 hours is 3.5. So that is 3.5 hours, or you can say 3 hours 30 minutes is still fine. Then the other one, what was the maximum voltage charge? So the maximum voltage, if you check on top on the side of voltage, you discover the maximum voltage was this here. So here you just go this side and go find out the voltage here between 8 and 10. So between 8 and 10 it's 9. So the maximum voltage is 9 volts. So 9 volts. All right, we proceed. Part B, if the working current of the phone is 0.6 amp, calculate the number 1 charge accumulated by the phone in 2 hours. Okay, charge is given by current times time. Now the current they've given us 0.6 amps multiplied by the time is 2 hours. Now you just have to convert 2 hours to seconds. So to convert 2 hours to seconds, you multiply it by 3600, so that it becomes in seconds. So when we do that, we're going to find 2 times 3600, that is 7200 multiplied by 0.6. 7200 multiplied by 0.6, we get 4320 coulombs. So that is the charge that we find for the data given. So after you find that charge, the second question is asking us to find the power of the phone when fully charged. Now power is given by voltage times current. Remember, the total voltage was what? 9 volts. Then the current they gave us was 0.6 amps. So what is 9 multiplied by 0.6? We get 5.4. Power is measured in what? Watts. Right. So that one has been dealt with. We proceed. We look at another question. B8, figure B8.1 shows a coil of insulated wire wood around a U-shaped core AB connected to a battery to make an electromagnet. Alright, state the property of end A. So the property of end A, look at end A. So this is our end A. Now what do you think is that property of that? So the property of NA is it's a north pole. So end A is a north pole. So end A is a north pole. Alright. Then describe one way of increasing the strength of this electromagnet. How can you increase the strength of an electromagnet? So the strength of an electromagnet can be increased by increasing the electric current. So that is one way. So it can be increased by increasing the electric current. Can be increased by increasing the electric current. So that is one of them, but you can also say, for instance, increasing the number of turns in the coil, or using a soft ion for the coil. So you just pick on one, then you are good to go. Okay, you proceed, you look at another question, part C. What material must be used for the coil? So the material should be used for the coil here is a soft iron. So we should use iron. So it's a soft iron, so it is a soft iron. That's the material which you should use. Justify your answer. Why should we use soft iron? Why? Because soft iron can easily magnetize. So it's easy to magnetize. Okay, magnetize and demagnetize. So it's easier to magnetize and demagnetize. So that's the reason why. So it's easier to magnetize and demagnetize. Right, we proceed, we go to another question. Now this is question 9. They are saying define half-life. Now half-life can be defined as the time taken for a radioactive nuclei to have its mass reduced to half its original mass. So it's just time taken. So it's a time taken. So half-life is time taken, alright, for a radioactive nuclei. So radioactive, so a radioactive nuclide, okay, to have its mass reduced. So to have its mass reduced to half its original mass. To half its original mass. So half-life is the time taken for a radioactive nuclide to have its mass reduced to half its original mass. Alright. The second part, iodine decays by emitting a beta particle to produce a new element, which is Xe and a gamma ray. Now let's do this. We have iodine, which is like that. So we have 132 here, we have 53 here. So now this iodine decays. So they are saying this iodine is going to decay and it is going to produce xenon, and apart from that it's going to produce a beta particle and it is going to produce a gamma particle. Alright, and basically there is also some form of energy because it's decaying, so even energies are produced. So to complete this equation, a beta particle is a fast moving electron, so it's like this, 0, -1, then gamma 0, 0. So what we do here is we say 132 minus 0 minus 0, we get 132 here. To find for this one, we say 53 minus -1, that's 54. 54 minus 0, that is 54. So meaning this is an equation for this decay. That's how you can write a decay equation. Alright, from there give one property of a beta particle. One of the properties of a beta particle is that it is negatively charged. So it is negatively charged. So that is one property of it. It is negatively charged. Then mention one medical use of radioactive substances. Now these radioactive substances can be used to treat cancer. So in the treatment of cancer, so we can use radioactive substances. Then explain the effect of radioactive substances on the environment. So one of the effects is they are going to cause what we call radiation pollution. That is a very serious effect, and they can also cause health related challenges. So they can be hazardous to our health. So health hazards. So they can also cause health hazards. Okay, so that has been answered. We then move on to part C. So part C, answer any two questions from this section in the separate answer booklet provided. Figure C 1.1 shows the velocity and time recorded for an athlete running in a race. The mass of the athlete is 75 kilograms. Then plot a velocity time graph for results recorded in figure C 1.1. Okay, now here I'm going to give a guide on how best you can go about this. It's not that difficult. Okay, since I don't have a graph, but I'm going to give a guide. So in here they've told us to say the mass of this athlete is 85 kilograms. It's very important to note that. So basically, whenever you are plotting something, a graph or anything, so you should you will do that. So let's say we're plotting a graph like that. So you should have your x and y axis. First, that's important, your x and y axis. So on your y axis, you should put velocity in meters per second. So this is why you put your velocity. Then this is why you put your time. And what are the unit time in seconds? So you just get this. Velocity meters per second should come here. Then the time should go there. Then your graph should have a title. And what is the title of the graph? It's a velocity versus time. So you should put your title somewhere here. The title of the graph is velocity versus time. Then you put now the numbers here. Now it depends with the graph that you have. You can actually put some numbers where you say from the way it is here from 0 to 9 time, you can demarcate your time here very well. So let's say 1 2 3 4 5 6 7 8 up to 9. Then velocity goes up to 10. Then you can spread it out 1 2 3 4 5 6 7 8 9 10, all the way up to 10. Then what we can do now, you start plotting 0 to 0. So we'll be somewhere here. 0 is there. Then you go on 1 to 3.5, 1 to 3.5, somewhere there. Then from 1 to 3.5 you go to 2 to 7.1. So we have 1 2 3 4 5 6 7, 7.1 somewhere there. 3 to 8.2, 8 somewhere there. 4 to 9.1, 4 to 9.1 somewhere there. 5 to 9.5, 5 to 9.5 somewhere there. 6 to 9.8, so somewhere there. 7 to 10, 7 to 10, somewhere there. Then 8 to 10, somewhere there. 9 to 10.2, somewhere there. Then basically your graph, then you just join them, but this hasn't been a smooth one, but basically your graph should be something like this. So something like that. So your graph should be something like that. So once you do that, then you'll be able to get some marks on that. So ensure that it is neat. So you can try it out, then you can show me what you're going to find on a real graph. Just that I don't have the graph at the moment, I would have shown you how it's supposed to go, but basically that is how it's supposed to go on a sketch. So that is just a sketch. Then calculate the acceleration of the authority in the first 2 seconds. Now that one is straightforward. Acceleration is equal to final velocity minus initial velocity over time. Now in the first 2 seconds, meaning what happened? Now you go here 2 seconds, then you check where your graph went. So here you check somewhere there. So if you check somewhere there, what are you going to find? So from there you're going to find that it was somewhere at 7.1. Listen, so you can come here. So this is 2, then it was at 7.1. So in the first 2 seconds it was at 7.1 minus the initial, it started at 0 here, then the time it took is 2 seconds. So 7.1 divided by 2 seconds, what do we get? We're supposed to get about 3.55 meters per second squared. So this one is our acceleration in the first 2 seconds. Then calculate the force that caused the acceleration in the first 2 seconds. Now force is given by mass times acceleration. Now remember, if I take you back, the mass was given us to be 75 kilograms, then the acceleration is 3.55. Then when we multiply those two, we should get about 266.25 newtons. So 266.25 newtons. Then from there now we proceed to finding the other one. Kinetic energy during the first 2 seconds. How do we find kinetic energy? So kinetic energy is given by half mv squared. So half multiplied by the mass is 75, then the velocity that it took. Now it's for the first 2 seconds, so we still get the 7.1. We still get the 7.1. So we're getting the 7.1. Where are we getting it from? So they've told us to say in the first 2 seconds. So you go where the 2 seconds is. This is 2 seconds. The velocity there is 7.1. So 7.1, then you proceed now to do your calculations for kinetic energy. So remember, we are finding kinetic energy. Let me just go back to the kinetic energy. So kinetic energy is equal to that. So now we are going to multiply half multiplied by 75 multiplied by 7.1. What do we get? So if we multiply that, we should get about okay, let me just get my calculator. So 0.5 multiplied by 75 multiplied by 7.1. So we should get about 266. So we should get about 2 for kinetic energy. Are we getting the same as force? 266 0.25. This is JAWS. Okay, let me just confirm. We got for the force that caused acceleration, what did we get? We got 266. Okay, let me just try that one out. So we have half of 75 multiplied by 7.1. Let me just do it again. So half of 75 multiplied by 7.1. Okay, then the other one, that one we're doing was 75 multiplied by 3.55. so there we are getting the same answers. So 7.1 multiplied by that. Alright, so they are the same answers we are getting. So 266.25. So 266.25, then that is joules. So energy is measured in joules. So just ensure you pass through this. So kinetic energy is given by half mv squared. So I've seen the velocity should be squared. So that is where the mistake came from. The velocity should be squared. So now the velocity should be squared. So now we say what is 7.1 multiplied by 7.1. Once you find that, multiplied by 75. Once you find that, multiply by half. So we should get about 1890.38. So the final answer should be 1890.38 joules. So this should be the final answer. So I forgot to square. On the formula there is a square here. Very important. So these are the final answers, but on the graph I'll emphasize you try to use a real graph paper. Question C2. Figure C2.1 shows the learner viewing an activity over a whole fence using the instrument shown in figure C2.1. So that is what we have there. Then we have a question that has been given to us. Now let's check out the diagram that we have. So that is what we have here. Then we check out. They are saying name the instrument used in figure C2.1. Now the instrument that is being used here in figure C2.1, it has a special name that we call it a periscope. So we call it a periscope. So in figure C2.1 we call it a periscope. Then copy and complete figure C2.1 by drawing a ray of light to show how the learner viewed the activity on stage. So you just copy the same diagram. I'm not going to copy it because I'm writing on the same. So what I'm going to do is that I'm just going to draw. So after you copy it, then what you're supposed to do is you're supposed to draw how the ray of light is supposed to come. Now the people are here, so it's actually coming from there. Now look at what will happen. If it comes, so it will come, let's say if it strikes here, somewhere here, from there, then it's going to be like that, to come there, then it will go there. So then we can show direction. This is the direction that it is taking. This is the direction that it is taking. So I think that is what you're supposed to put there. Copy and complete. So by drawing a ray of light, so to show how the learner viewed the activity on stage. Okay, so that is basically how that one was done. That is basically how that one was done. All right, then from there now we proceed. We look at another question. Figure C2.2 shows a glass prism with one face labeled AB. The refractive index of the glass prism is 1.5. Okay, define critical angle. So this is just a definition. How do we define critical angle? So critical angle is defined as an angle of incidence that gives an angle of refraction of 90 degrees. So an angle of incidence that gives an angle of refraction of 90 degrees. That is critical angle. So we define it as an angle of incidence, that gives, so that gives an angle of refraction of 90 degrees. So that gives an angle of refraction of 90 degrees. So that is critical angle. So once critical angle has been defined, copy and complete figure C2.2 to show a narrow beam of light which is incident on the face AB of the glass prism until it emerges out of the prism. So now here we just want to see what is going to happen. Want to show a narrow beam of light which is incident on the face AB until it emerges out of the prism. Now I'm going to use the same diagram so that I'm able to show you. Now this is what will happen. It is going to move at an angle perpendicular to AB. Look at what will happen. It will come, move like that in a straight line, hit here, and then it's going to turn like that. This is what will happen. Now this is a 90 degrees and it is moving in that direction, then it's going to turn and come out in that direction. So that is what you are supposed to put just. That is what you are supposed to put just, then you are good to go. Okay, let's see the other question. After we've copied and complete, calculate the critical angle of the glass prism. Okay, how do we find critical angle? Let's find critical angle. Critical angle, so this is the formula for critical angle. So critical angle is equal to sine inverse 1 over the refractive index. So sine inverse 1 over the refractive index is 1.5. So what do we get? So this becomes so the critical angle, the sine inverse, if you do that one, you should get about 41.81 degrees. It's an angle, so you get about 41.81 degrees. So that is what we get for critical angle. So after critical angle has been found, give two uses of total internal reflection. So total internal reflection can be used by, so we're saying can be used by doctors. That's the first. So it can be used by doctors for what we call endoscope. So they can be used by doctors for endoscope. Then they can also be used for optic fiber. So optic fiber, then etc. So you can put any other uses of total internal diffraction that you can that you know of. All right. Then we proceed to the last part. The first one is on the definition. Define radioactivity. How can you best define radioactivity? So this, I won't write it, I'll just define. Radioactivity is defined as the spontaneous disintegration of the unstable radioactive elements emitting radioactive emissions. So you can define this as the spontaneous disintegration of the unstable radioactive elements emitting radioactive emissions. But you can also define it in different ways, so you are free to pick up a definition that will be easier for you and write that one. So we're going to go to part B. Radionuclide decays to form polonium by emission of an alpha particle. Write the decay equation. Now we have radon 22 to, then we have 86 here. Okay, let me just write it properly. So let's do that. Then we now say we have radon, okay, 222, then 86. This one decays to emit polonium. Polonium isn't supposed to be Pa, it's Po. Polonium is Po, by emitting an alpha particle. So an alpha particle is just defined as a helium nuclei. Of course, some amount of energy will be formed. Right, so now this is what you do. 222 subtract 4, you get 218. Then 86 subtract 2, you get 84. So that is how you can write this decay equation. That's how you can write that decay equation. Alright, from there now we go to part C. Figure 3.1 shows the results obtained to determine the half-life of the radioactive element. So that is what we have. Again, this one is on plotting. Like I said, I'm going to give a guide. Whenever you are plotting, you need to come up with the y and x axis. The y and x axis. Then you need to title your graph. So the title of your graph, so they're saying plot a graph of activity against time. So the title should be activity against time. Then you say always time will be here, then activity will be on the other end there. Then you can start plotting. So you can put some random, not necessarily random digits, but you can follow them by seeing the trend in which we are going. So time is from there up to there. Then we have activity counts per minute up to that. So you can say, for instance, we have that up to the highest. So this one, it is decreasing with time. So we have that, we have 0.5 to 30. So it's coming out like this. So at the end of the day, this is what you are going to observe as you are plotting. So you plot that. So this is just an approximate one that I'm making. You plot, you do that. So let's say, so you come here, you plot there, you plot there, you plot there. So at the end of the day, you're going to come up with a graph that is similar to this one. So it is decreasing with an increase in time. So now, this is the type of a graph you're going to come up with. So after you label it and everything, you're now going to get those formats. Then determine from the graph the half-life of the element. Now to just get the half-life, this is what you do. So you look at to get half-life, you're going to look at the highest number that we have. So the highest number that we have here on the activity is 42. Then you get half of it. So what is half of 42? Half of 42 is 21. So you look for where 21 is. If 21 is there, you go and meet somewhere here, you go and meet the graph. Then you come down so that you can check for the time that is there. So you check for a time that is there. So once you see that, you should find half-life to be 1.25 minutes. So this is what you're supposed to find, 1.25 minutes, once you plot this one on an actual graph. So once you plot this one, you should find about 1.25 minutes. So that is what we are supposed to find. So once you find that, you are well and good. Okay, state one possible source of background radiations. Okay, so one possible source of background radiations, what can we say? So one possible source of background radiation is what we call cosmic rays from the sun. Cosmic rays. So that is one possible source of background radiation. Of course, there are many other sources, such as radioactive rocks. So these are also sources. So radioactive rocks. So we have that. So that is basically what we have there. That is basically what we have. Do we have any other question? I guess this was the end of it. So try the graphs and then you see what you're going to find, but those should be the solutions that you are supposed to find. Right.